Okay, so we continue with the quantum Teichmüller theory. So, and last time we finished solving W and R hat, and so we have constructed R hat in unitary of L2 of R, and W hat in the unitaries of L2 of R2, given by, so R hat, so what was it? It was a zeta E 3 pi I Q squared E pi I P hat plus Q hat squared. I think it was this formula. Zeta cube was -1, and W hat is given by phi of Q1 hat minus Q2 hat plus P2 hat multiplied by E minus 2 pi I P1 hat Q2 hat, where phi of x is a Faddeev's quantum dialog function, any x in reals. So the argument of this function is real because this is self-adjoint operator. So we need just the restriction of the function phi to real line. And now the first theorem. Today is lecture number 11, I guess. 11.1 tells the following thing. So the triple V equal L2 of R R hat W hat is a basic algebraic system in the category of Hilbert spaces. Is a is a projective basic algebraic system in the category of Hilbert spaces with a, say, completed tensor product. So the completed tensor product means that V tensor hat V here means L2 of R2, right? So we can't stay with the algebraic tensor product because the tensor product of L2 of R times L2 of R is not L2 of R2. So we have to complete it now. Okay, so that's a statement which is not difficult. As soon as we know all the properties, we have studied for function phi. And so let us see how the proof goes. So the R cube is one that we know, right? So that has been checked. Actually, the normalization factor zeta was fixed from that condition. So it's okay. And then the pentagon 5-term identity for W. So W12 at W23 should be equal to W23, W13, W12. So let us try to substitute let me exchange the left-hand side, right-hand side. So W12, W23. Let us call this left-hand side, right-hand side. So let us start with the left-hand side. Then we substitute the formula. Then we get phi of Q2 minus Q3 plus P3 E minus 2 pi I P2 Q3. Then phi of Q1 minus Q3 plus P3 exponential minus 2 pi I P1 Q3 and one more term, phi of Q1 minus Q2 plus P2 E minus 2 pi I P1 Q2. And now we are going to move all exponentials to the right-hand side, modifying, if necessary, the arguments of phi using the Baker-Campbell-Hausdorff formula. So the first phi stays intact. Then the second, so we start conjugating the argument of phi. So first we conjugate Q1. But the exponential does not depend on the first space, so Q1 doesn't change. Then Q3. Q3 also doesn't change because the exponential depends on Q3. So minus Q3. Now P3. P3 will change, so we just use the formula. It will change P3 plus the commutator of that with P3. And all higher commutators will not contribute. So we write minus 2 pi I P2 commutator Q3 with P3. And then we put these two exponentials together, minus 2 pi I. So they commute, right? Q3 commutes with Q3, P1 commutes with P2, and so on. So we write P1 hat plus P2 hat Q3 hat, and then we just copy the last term without changing. So this term is I over 2 pi. So we continue. Phi of Q2 minus Q3 plus P3. Phi Q1 minus Q3 plus P3, and minus I times I gives 1, 2 pi goes away, so plus P2. And now in the third term, we again move the exponential through the function of phi by modifying the argument. So we can just observe that P2 commutes with the exponential, so it does not change. But Q1 minus Q2 commutes with P1 plus P2, right? Because P1 times Q1 produces some scalar factor, but P2 Q2 with minus produces the same scalar factor with opposite sign. So the net effect, everything commutes. So we leave the phi without changing. And all exponentials meet together, minus 2 pi I P1 plus P2 Q3 E minus 2 pi I P1 Q2. So that's we stop here for the left-hand side, and we continue with the right-hand side. Phi of Q1 minus Q2 plus P2 E minus 2 pi I P1 Q2 and W23 Q2 minus Q3 plus P3 E minus 2 pi I P2 Q3. And now we need to move only one exponential through one phi, and Q2 commute with P1, Q2, Q3. Anything depending on 3 depends, of course, with the operator acting in 1 and 3. So nothing changes. It goes through freely. And now observe that. That E minus 2 pi I P1 hat Q2 hat times E minus 2 pi I P2 Q3 is equal to that. Let me separate this to make it clear why it is so. So I put first this term, P2 Q3, to the left. Then I put in the middle minus 2 pi I P1 Q3. And then I put minus 2 pi I P1 Q2. So you see that the leftmost term here coincides with the rightmost term. Rightmost term in the left-hand side coincides with the leftmost term in the left-hand side. And then if we call P1 minus 2 pi I A P1 Q2 by A, and this term by B, then let us calculate the commutator. So then A commutator B, what is it? So minus 2 pi I squared. And then non-trivial commutation happens only in the subspace 2. So we pull out the P1 hat, Q2 P2 commutator, and Q3 stays outside. So this is equal I over 2 pi. So by simplifying, we get minus 2 pi I P1 Q3. And let us call this C. And now we check that we see that AC equal BC equals 0. why it is so. If we try commute A with C, then P1 is common thing, right? It commutes with itself, but Q2, we have Q2 there and the Q3 here, so nothing else to commute non-trivially. And likewise for B and C. So that means that E to A, E to B is equal E to B, E to A, and a commutator AB by Baker-Campbell-Hausdorff. And this is exactly the identity we are checking, right? Because the C is nothing else than the term in the middle. So, equation 2. So 2 is the equivalent to the identity for the remaining part of the identity. So phi of let me call this combination capital Q, this combination capital P. So we have a capital Q. And in the middle, if we add P and Q, then we get here P plus Q. Right, so we have Q1, it's okay, minus Q2 cancels Q2 here. Then we have minus Q3 and P2 plus P3. So in the middle we have exactly P plus Q. So the identity we are trying to check is equal phi of Q, phi of P plus Q, phi of Q equal. And here we see clearly that this is again P, and this is a Q. So phi of Q, phi of P, phi of Q. And now let us commute capital P with capital Q. By using substitutions, Q2 hat minus Q3 hat plus P3. So that's a Q. Q1 hat minus Q2 hat plus P2. Q2 minus Q3 plus P3. So one, in the second term, there is nothing depending on 1, so this does not contribute. 3 does not contribute as well. And then the only contribution comes from Q2 commutes with itself, so this does not contribute. So this is the P2 Q2, which is 1 over 2 pi I. 1 means identity operator. But the essential thing that capital PQ satisfy the same commutation relations as a small p hat and a small q hat. But we have seen that this 5-term identity is satisfied for little p and little q. At least we checked it up to numerical constant, but I claim that the numerical constant is 1. So, this equation is verified.
So sorry, there should be a P instead of this Q, right? It's phi Q, phi P plus Q, phi P, or am I mistaken?
Where?
The second Q. Yeah, yeah. This is Q or Q?
This is P. Okay. Thank you. Thank you. Yeah. Okay, so that has been checked. And then the third equation is a mixed equation. So what was it? Yeah, it's somewhere many lectures back. Being the definition of the basic algebraic system. Yeah, so what we have to check is R1, R2, W21, R1 inverse W12 equal permutation 1, 2, but with some coefficients psi. Projective means that we have to check this up to numerical factor. Okay, but we have to check it with operators with heads. This is a standard permutation operator. So let us try to do this. So part 3. So we have R1 hat, R2 hat, phi of. So now we have to write W21. So which means that in the formula we have to exchange 2 and 1, which means that we write my Q2 minus Q1 plus P1. Right? And the E minus 2 pi I. So we had P1 Q2. So it should be P2 Q1. Then we write R1 inverse. Phi of Q1 minus Q2 plus P2 E to minus 2 pi I P1 hat Q2 hat equal some psi, or under question mark, since we don't know yet if this is true or not, P12. So what is the action of R1 when it conjugates things? R1 inverse in the middle, yes, exactly. So where it could be, which lecture? Yeah, so here they are. So the R1 hat conjugates Q hat and gives P hat minus Q hat, and R hat conjugates P hat and gives minus Q hat. Okay, this is a property of R with respect to the Heisenberg operators, and then we can use this to move this r hat through here, or maybe this r hat through this phi first. So 3 is equivalent to r2 stays intact. Now we move r1 hat through the argument of phi. Phi of q2 is not changed. Now q1, minus q1 should become minus this. Minus p1 plus q1. And p1 should become minus q1. Minus q1. And then we can move through this exponential also. Minus 2 pi I. P2 stays intact. And q1 becomes p1 hat minus q1 hat. And the r1 disappears because it meets its inverse. So we write the rest minus q2 plus p2 e minus 2 pi I p1 hat q2 hat equal question mark psi p1 2. So we have a simplification here. Q1 goes away. And then we do as we did in step 2. We move this exponential through this phi. So what this becomes? So phi of q1 hat. How it changes? q1 we have to commute with this. It produces plus 1 over 2 pi I. Right? P1 commutes with q1, produces 1 2 pi I, and we have to put the multiplication factor, minus 2 pi I, p2. And then we treat minus q2. Minus q2 plus commutator of p2 with q2 gives 1 over 2 pi I, and we multiply by the rest. Minus 2 pi I, p1 minus q1. That's the middle term, and p2 commutes, so it does not change, plus p2. And we put the exponential to the right-hand side, e minus 2 pi I, p2, p1 hat minus q1 hat. And so we have, let us simplify the argument. Yeah. So q1 hat, here we have minus p2. I think I miss one parenthesis here, right? So minus q2. And here we have minus p1, one more minus, plus p1. And the minus plus q1, so minus q1 plus p2. So we have, we simplify q1 and p2. So the answer is that, so 3 is equivalent to R2 hat phi of Q2 minus P1, phi of that P1 minus Q2, and the rest is product of two exponential, minus 2 pi I, P2 P1 minus Q1 times that exponential, E minus 2 pi I, P1 hat Q2 hat. If this is equal to P12. And now we can remark that we get here inversion relation. Remember that the Faddeev function satisfies phi b of x, phi b of minus x. It was a phi b of 0 squared e pi I x squared. Right? We have this. And phi is just phi b here. Right? So we, and these arguments are exactly opposite. So this becomes, let me use the phi because it's more economical. I avoid writing b. P1 minus Q2, oh, sorry, 0 squared times Gaussian exponential pi I P1 minus Q2 hat squared. So we got something in the metaplectic group, right? Because everything is given by quadratic forms, exponentials of quadratic forms of Heisenberg operators. This is a distinguishing feature of the metaplectic group, which means that when we conjugate by those unitary operators, Heisenberg operators, they will be transformed linearly among themselves. Okay, so we end up with the identity R2 hat times E pi I P1 hat minus Q2 hat squared E minus 2 pi I P2 P1 hat minus Q1 hat E minus 2 pi I P1 Q2 hat, and this is equal, and the question mark, psi divided by phi of 0 squared. So I divide by this scalar factor here. So times the permutation. And now what we are going to check this because psi is not specified. So to prove this theorem, it suffices to show that this left-hand side conjugates the Heisenberg operators the same way as the right-hand side. So of course, we have a property that P12 Q1, let me put it, P1 Q1 P2 Q2 P12 minus 1, but it squares to 1 anyway, so but let me put it minus 1 explicitly to see that we have a conjugation. Then P1 becomes P2, Q1 becomes Q2, P2 becomes a P1, and Q2 becomes a Q1. So that's a defining property of the permutation operator. And then we have to check that the left-hand side gives the same transformation law. So let us try. So let's call this A. So A, P1 had A inverse. So first we conjugate by this exponential. P1 commutes with everything, so this exponential does not contribute. So then we have conjugate P1 by this exponential, and this contributes. So it becomes a P1 plus a commutator of that with P1. So P1 minus Q1 commutes with P1 as an inverse of 2 pi I. And then we have to multiply by this coefficient. minus 2 pi I P2. That's okay. And now the last term, we have to commute this by this. So let us simplify first. Okay, so we have to put R2 hat E pi I P1 hat minus Q2 hat squared. And from this side, the inverse of it. E minus pi I P1 hat minus Q2 hat squared R2 hat inverse. Okay, do you follow me? So we conjugated by this, which was trivial, and then we conjugated by this, which gave the middle term. And then the conjugation with the rest of the operator stays from two sides here. Now we can simplify. So now we have to conjugate P1 by this. It is trivial because this commutes with P1. So R2 hat stays. So P1 survives, but the P2 will be modified. So minus, so P2 and plus commutator of this, which is plus 2 pi I. So we have to differentiate just the P1 hat minus Q2 hat. And the commutator of that with P2. And minus Q2 commutes with P2 just as inverse of 2 pi I. 2 pi I. Parenthesis. And the R2 inverse. So we simplify, and then we have some more simplification. So which is R2 hat. P1 goes away, because we have a P1 here, we have minus, and here P1 here. So what remains is Q2 minus P2. Hat minus 1. And now again we can use these relations in the second subspace. So we write Q2 becomes P2 minus Q2 minus P becomes a plus Q2. And as you see, we safely arrive to P2. That's here. And shall we go on with this? Or you can do yourself? Okay, we stop here, and the rest is the exercise. Okay, so that's the thing. So we have checked that we obtained the basic algebraic system, and then by using the fact that any basic algebraic system gives rise to a representation of the mapping class group, so we come to the conclusion. The L2 of R hat W hat gives rise to a unitary projective representations of the mapping class groups of all punctured surfaces of finite type with the negative negative Euler characteristic. Also, saying differently, for any punctured surface admitting ideal triangulation. So we have a unitary representation. And this is actually the first indication of the TQ of T we are heading to. But already on this level, we can say that what will be eventually the quantum invariance of that TQ of T, at least for a restricted class of 3 manifolds. And later, hopefully, because it remains 2.5 lectures, right, from now, after the break. So hopefully, we will see that that the traces of the trace of f of f okay, let me put it this way. Absolute value of the trace of f, let me put it mapping class projective representations f. Okay, so capital F is the representation we are talking about. Hopefully we will see that the trace of that operator, absolute value, is in the case of the surface as G1, only one puncture. Okay, when in the case of once punctured surfaces of the surfaces is a topological invariant of the mapping torus. Mapping torus MF obtained by surface S cross, so let me put this, S equal S cross interval quotient by x comma 0 equivalent to f of x comma 1. So we take a product of the surface. For example, the punctured torus. In the simplest case, so we take a punctured torus, multiply it by the interval, and then we get a manifold with boundary, where the two boundary components correspond to 0 times surface and 1 times surface. And we identify these two boundary components through the homeomorphism of the surface S, which represents the mapping class F. We choose a representative of our mapping class. Remember, F is the element of the mapping class group, so it is represented by a diffeomorphism of the surface, which doesn't move the puncture. And so we quotient our manifold, but remember that the puncture is an absent point, right? So the vertex is not included. But if we include this point, so what is the image in the mapping torus? It's a circle. So if we remove this point, then we have to remove that circle. So so it is a 3 manifold. It's a complement of the mapping torus over closed torus of that circle. So it will be an invariant of a knot. This circle represents a knot in this mapping torus. And this trace, absolute value of it, will be the invariant of that knot in that 3 manifold. But at this stage, of course, we can now try to calculate that quantity. But at this stage, it remains to be proved that this is actual invariant of the 3 manifold. OK, so we continue after the break. So it cannot be TQ of t in the usual sense of the word, because we know that if we take the list of axioms of a TQ of t, then necessarily the vector spaces associated to surfaces will be finite dimensional. And in our case, we have infinite dimensional vector spaces. So if we are going to construct a TQ of t, at least it will, at best, it will satisfy some weakened version of the axioms of a TQ of t. But it will be still this weakened set of axioms will be enough to show that that trace is a topological invariant. But remember that this is a trace in infinite dimensional vector space. So if we take, for example, identity mapping class, so this is identity operator, surely this is infinite. But it happens so that this infinite is invariant. The invariant, associated invariant in this theory is infinite. But most often, at least under some hypothesis, there are reasons to believe that as soon as f is a pseudo-Anosov, this trace is always finite. Okay, so this is the last chapter of our course, which is called the Teichmüller TQ of t. And to construct this TQ of t, so we have to know a little bit more about the Faddeev quantum dialog than we know. Apart the properties we know already, we need to know more. And the reason why comes from the fact that we have to abandon the operator world in TQ of t. What we do in TQ of t? We do some combinatorial, choose some combinatorial setting, and here the setting will be triangulated 3 manifolds. And then we have to associate some weight functions to tetrahedra. Then we multiply these weight functions over all tetrahedra over a given triangulation. And then in the usual Turai-Vero case, we have to sum over all possible colorings of edges of the triangulation. In our case, we will color the triangles of the triangulation, but we will color them by just real numbers. So we will have to integrate over all colorings by real numbers. But to do so, we have to identify what are the weight functions of tetrahedra. But in the representation, we have unitary operators. And we have a pentagon 5-term operator identity for the quantum dialog logarithm, which will correspond to Pachner move in a triangulated manifold. But to see how the Pachner move is realized, we have to convert the operator identity into an integral identity, because summations will be integrations. So we start from that problem now. So we are going to convert the pentagon identity to an integral identity. So let me put it as a lemma, because this is some kind of not very important identity, because it is some just a preliminary identity with which we will be working. So the enumeration is how we enumerate. Separately, Lemma's theorems? I don't know. We had theorem 1, right? 11.1, so let it lemma be number 2. Okay, so let phi r to t, remember t is a unit circle, be a function satisfying the operator 5-term identity. Phi of p hat, phi of q hat equal phi of q hat, phi of p hat plus q hat, phi of p hat. And of course, we think of, in principle, we don't know if phi function is unique function which satisfies this identity. So we will do it not specifying explicitly, but of course we have to think of phi function. Satisfying the operator 5-term identity, as usual with standard Heisenberg operators. And then the following integral identity is satisfied. And what is the integral identity? It is E 2 pi I st phi tilde of s, phi tilde of t is equal integral over real line, phi tilde of t minus u, phi tilde of u, phi tilde of s minus u, e pi I u squared du. Yes, and where phi tilde of x is by definition the Fourier transform of phi. Y e minus 2 pi I xy dy. And of course, by assumption, we are on the unit circle, so we're integrating a oscillating function. So the integral, of course, does not converge absolutely. So the integral should be thought in the distributional sense, where the Fourier integral should be interpreted, or no, is interpreted, is interpreted in distributional sense. And more precisely, tempered distributional sense, right? Because we treat phi of y as a tempered distribution. What is tempered distribution? In particular, any locally integrable function of at most polynomial growth corresponds to a tempered distribution. But tempered distributions form the topological dual of the Schwarz space of of smooth functions decreasing rapidly, more rapidly than any polynomial growth. And the Fourier transformation is well-defined map of the Schwarz space to itself. So by transposition, Fourier transform is well-defined in the space of all tempered distributions. And phi of y lives on the unit circle, so it doesn't grow at all. So in particular, so it is a tempered distribution. And that's a statement. So you see, it's just a single integral identity for the Fourier image of phi.
So if we want to compute it, can we approximate it by Schwarz function, or we can just compute it?
We will, very good question, and actually we will do so. But so far we proceed just on the distributional level, but we will have to calculate this Fourier transform, and we will calculate it exactly the way you say. Okay, so proof. So we, of course, by inverting the Fourier transform, we have a formula phi of y e 2 pi I 2 pi I xy dy. And now we just going to substitute in the operator identity this integral representation for each of phi. So let me call this again this was this is the right hand side, this is the left hand side, and let us calculate the right hand side. So phi of, I will integrate with t. So I will adapt to the formula we are heading to. So I will integrate over t e 2 pi I q hat t. Right? That's for the first phi. Then we write the phi of u e 2 pi I p hat plus q hat of u. And the phi of s e 2 pi I p hat s. And we have a triple integral ds, dt, du. And we collect the similar terms. So, but first of all, we have to split the middle exponential by using the Baker-Campbell-Hausdorff. So e 2 pi I p hat plus q hat of u. What is it? So we can use our trick of symmetric factorization. For example, we take we leave p as it is, and then we split half of q to the left, half of q to the right, then no correction terms, right? So we write my pi I q hat u e 2 pi I p hat u e pi I q hat u. And then we can commute, we can move p hat to the right through this q hat, and then get the formula. But of course, you can do in other way, just by applying the Baker-Campbell-Hausdorff directly. Okay, so we commute, we pass this through this, so we get e 2 pi I q hat u, e 2 pi I p hat u, and what is the correction term? It is a e pi I u squared. And now we continue with this equality. So now you see that 2 pi I q t meets 2 pi I q hat u, and likewise for p. So we can put them together. We get phi of t e 2 pi I q t plus u, phi of u, phi of s, e 2 pi I p hat s plus u, and that's it. ds, dt, du. And the last thing we do here, we shift t by minus u and s by minus u to clear up the coefficients of q hat and p hat. Integral R3 phi of t minus u, phi of u, phi of s minus u, e pi I u squared, and here we have two exponential, 2 pi I q hat t, and the e 2 pi I p hat s, ds, dt, du. Okay, so the neat effect of what we have done, we have collected something numerical times operator exponentials put together, and all q's and p's separated. So effectively we have given the representation of operators, arbitrary operators in L2 of R, in the integral form which we used to define this regularized trace, if you remember. We had this some 2 weeks ago maybe. And now we do the same for the left-hand side, but the left-hand side is much easier. So let us see, left-hand side is equal. So we start by s, phi of s e 2 pi I p hat s, phi of t e 2 pi I q hat t, ds dt, integral over R2. And now we, because in the right-hand side we put first q hat and after p hat. So we have to exchange their order. So we get phi of s, phi of t, and the result of exchanging is 2 pi I st, e 2 pi I q hat t, e 2 pi I p hat t, p hat s, ds dt, integral, double integral over R2. And now we have operator equality, which means that the coefficients of integrals should be equal, right? Because this representation is a unique way of writing an operator. So we come to the integral relation. Integral relation. It's equivalent. And we throw away integration over ds dt and equate the rest. So we have this. But remember, everything now it should be understood in the distributional sense. So strictly speaking, this equality tells us that we have to take a test function in R2 and contract the left-hand side with the test function, and it will be equal to the contraction of the right-hand side with the test function. Okay, now our goal is to calculate Phi tilde. And this will be a theorem, because this is a formula very important. And this formula will be a formula which makes the phi df function even more remarkable. Because its Fourier transform can be calculated explicitly in terms of the same function. So you will see now the formula. So this is theorem. This is 11.2. So there exists a number zeta 0 in a non-zero complex number such that integral over r plus I epsilon phi b of u e minus 2 pi I u z du is equal zeta 0 e minus pi I z squared phi b of I over 2 b plus b inverse minus z. Where 0 is less than imaginary part of z is less than b plus b inverse half. Sorry, we have to insert here less than epsilon, and epsilon is less than b plus b inverse. Okay, that's the end of the theorem. And then just a remark. So zeta 0 actually can be calculated, but we will not do that here. Is given by e pi I over 4 plus pi I over 12 b squared plus b minus 1. So it's a pure phase given by this formula. And this is indeed a remarkable formula because now we can make, for example, we can send the imaginary part of z to 0, and the limiting formula will give us the distributional Fourier transform of phi of y, because we can put epsilon also very small. And but in this form, the integral absolutely converges. So let me put it second remark. So the integral in so let me put it Fourier integral in Fi converges absolutely. Okay, let us prove this. So let us check the second remark, right? We start from that. Now, so Fi is equivalent to real integral of phi b of x plus I epsilon e minus 2 pi I x plus I epsilon z dx. No, let us define this, right? I of z. We define just this. The objective is to show that I of z is the right-hand side. And let us see when x goes to minus infinity. When x goes to minus infinity, we know that phi goes to 1. It's last property number 5 in the theorem of last week. So phi goes to 1. And then we should look what happens with the exponential. So the real part of the absolute value of minus 2 pi I x plus I epsilon z behaves like e 2 pi x imaginary part of z. Because so the epsilon part does not contribute to the asymptotics; it's a constant. So we have minus I times x. So the real part is just oscillating part. So we plus I imaginary part minus I, and I become plus 1. So we write the rest of the coefficients 2 pi x imaginary x. And so this goes exponentially to 0 if imaginary part of z is positive. Because x goes to minus infinity. X goes to minus infinity. And now let us see what happens when x goes to plus infinity. When x goes to plus infinity, so we have to use the asymptotics of phi at plus infinity. But remember that we have the inversion relation, which allows to see the behavior of phi at plus infinity by knowing it behaves at minus infinity. So phi of x plus I epsilon is equal phi of x plus I epsilon phi of minus x minus I epsilon divided by phi of minus x minus I epsilon. And this is equal phi of 0 squared e pi I x plus I epsilon squared divided by phi of minus x minus I epsilon. But the denominator goes to 1 because x goes to plus infinity. Right? So minus x goes to minus infinity, and we know the asymptotics of phi at minus infinity. So this behaves like phi of x, phi of, so let me drop the coefficients. So I will only, okay, so phi of x plus I epsilon, absolute value, behaves like, so we should keep only the mixed term here, 2 pi I, so it becomes a e minus 2 pi x epsilon when x goes to plus infinity. But this exponential still contributes to plus infinity, and the contribution is the same. So, so phi of x plus I epsilon e minus 2 pi I x plus I epsilon z absolute value gives e minus 2 pi x epsilon, which comes from this part, times plus 2 pi x imaginary part of z. It's the same as before, right? So nothing changes. And we can write this as a minus 2 pi x epsilon minus imaginary part of z. And this goes to 0 when x goes to plus infinity because the imaginary part of z is assumed to be less than epsilon. So thus I of z converges absolutely. Absolutely. And thus I of z is analytic. in the strip imaginary part of Z bigger than 0 but less than B plus B inverse half. Okay, so so we have this, and we from now we assume that B is less than B inverse. Okay, so by this assumption we lose only 1 point, B equal 1. Okay, so but the proof uses this fact, and but if we have the opposite, then we know that the phi d function is symmetric in B inverse. So we exchange the role of B and B inverse. So we safely have again the same assumption. And now using this, we just write. The functional equation. So we have a phi of x minus phi b of ib over 2 equal 1 plus e 2 pi b x phi b of x plus ib half. And by analytic continuation, this functional equation is satisfied everywhere on the complex plane, except, of course, if we stay away from the poles. And so we can put here z. And now what we do is we just translate by half of b, phi b of z equal 1 plus e 2 pi b z plus ib over 2. Phi b of z plus ib. Okay, the same equation, which obtained by just a translation of the argument z. And now we can put z equal x plus I epsilon. So we have a phi b of x plus I epsilon equal 1 plus e 2 pi b x plus I epsilon plus ib half phi b of x plus I epsilon plus ib. Now we have prepared the formula for taking Fourier integral, at least the left-hand side. So we multiply by this exponential and integrate over x. So in the left-hand side, we will get immediately I of z. So let me leave for a while the definition of I of z. So I of z equal. And we just write the right-hand side. 1 plus e 2 pi b x plus I epsilon plus I b over 2. Phi b of x plus I epsilon plus ib e minus 2 pi I x plus I epsilon z dx. And we, of course, we can ask if we have an absolutely convergent integral. here, because it is not quite the I of z. But of course, the answer is yes, because the left-hand side is absolutely convergent. But this was identity, so this is obliged to be absolutely convergent. And it is, because, for example, at plus infinity, we have a epsilon plus b over 2 exponential damping factor, which compensates the growth because of this b, and using and also the fact that we have this inequality. Okay, but let us just proceed by integrating term-wise. So we have a sum of two terms here. So the first term becomes what? The first term is integral phi of u, where u lives in real line plus I epsilon plus b. Right, I'm changing the variable. This whole variable I called u. And so here we have a e minus 2 pi I u minus ib z du. Right? This is the first term. And for the second term, plus integral, still the same contour, I epsilon plus b, phi b of u. Now I have to change the variable here, so here it will be u. We need not half, the whole b here. So we have to subtract half of b. Right? And this term times e 2 pi I u minus ib z du. And so we end up, so now we can write this in terms of I of z. Right? This part is constant, so this is equal I of z times e minus 2 pi b z. Right? The first integral. And the plus I of what? So we have to collect the coefficients of minus, somewhere minus is missing, I think here. So we have to collect the coefficients of minus 2 pi I u. So it will be z, but shifted, because we have this term. So minus 2 pi I, so plus ib. Right? And we write the rest. The rest is e. Here we have minus 2 pi b z, this term. And here one more contribution given by minus pi I b squared. And now you see that we have shifted z by the quantity ib, and that we have to make sure that we stay in the domain of analyticity, which means that the imaginary part of z plus b should be less than b plus b inverse over 2. Which is equivalent to imaginary part of z should be less than b inverse minus b half. And as you see, our inequality allows to stay with this inequality, because imaginary part of z should be also positive. So if this inequality is not satisfied, then we don't have room for the imaginary part of z. But with this inequality, we have that room. And now what we see, so we already see that I of z satisfies the functional equation. So let us write this functional equation. So the I of z I can put together. So I of z 1 minus e minus 2 pi b z is equal I of z plus ib e that's minus, right? That should be minus, because minus minus becomes plus, but I squared is minus. So minus 2 pi bz minus pi I b squared. Now I can multiply by e 2 pi b z minus 1 equal I of z plus ib e minus pi I b squared. And is that correct? Yeah, that looks correct. And what we do is this. So let me define a combination C sub B, this combination, right? And then what I do here, I write this part as a E 2 pi B Z Z of minus CB minus 1. Yes, so first I shift by minus IB half. So I Z minus IB half E 2 pi B Z minus IB half minus 1 equal I Z plus IB half E minus pi IB squared. And now here I can insert minus I half B inverse. But the effect of inserting this term is changing the sign in front, because B inverse cancels B, 1/2 cancels 2, and what remains minus pi I, which is minus. So I put minus here, so nothing has changed. This is all this is a minus CB. And now, so we have E Z minus IB half 1 plus E 2 pi B Z minus CB. Now you are seeing, starting to see what is going on here. Minus pi I B squared, I of Z plus IB half. And now this we can replace by phi B of Z minus CB minus IB over 2 divided by phi B Z minus CB plus IB over 2. And now you see that this guy can be combined with this guy and this guy with this guy. So we simplify our functional equation. And then it remains to treat this constant term to absorb into redefinition of the rest. And that essentially will be very close to the end, but we don't have time to finish it today, so we'll leave it for the next time, and we start from here. Okay. Do you have any questions? Everything is clear.